Hi folks, welcome to lecture 1 of the Maths for Science 2 module, and in this lecture we're going to be taking a look at functions in general. What is a function as opposed to an equation, which we were looking at last semester. So really a function relates an input to an output. So there's three basic parts. There's the input. This is what we feed in. And usually the input is called x. Now, as we'll see in later slides, we can use any letter. But in a general math sense, x is our input. It gets fed into the function. This is the relationship. We'll be examining 7 of these. And then an output is produced. And that, as I said, we usually call y. This is what we're interested in though. What's going on in here? What type of function are we looking at? Is it linear? Is it quadratic? Is it exponential? As scientists, it's very important to be kind of familiar with the main functions and identify, is the system I'm examining, is it typically a quadratic function, maybe a cubic function? We have to, as scientists, be able to determine these facts. So multiply a value by 2. So a value is really our input. Multiply an input by 2. That's a function. It can be written as 2x. And here we have some inputs. We choose the inputs. We're taking a look at the values 0, 1, 7, and 10. We apply the function. And then we get our output, which I'll call y. So here's our input going in. This is our function. And then we have our output. Now, we write these as ordered pairs. The input and its associated output are written as a coordinate. 0, 0, 1, 2, 7, 14, 10, 20. Note how the input is always written first, guys. That's absolutely vital. Everything hangs on your being able to discern what's my input in this scenario, what's the output, etc., etc. So we'll take a look as we go along. The input is always written on the left and the output is always on the right of these coordinates. Now the values of the input are called the domain. So 0, 1, 7, 10, that's the domain of this function. These are the values we're interested in. And then the outputs are called the range. We won't be using this terminology very much. It's just to be kind of au fait with the language used. So the inputs are called the domain. The outputs are called the range of the function. So these are the functions we're going to be examining. Linear, quadratic, cubic. Note here, the only thing that's different, changing, is the power on x. And that's what defines the function. What's the highest power on x? Often we'll call these rational functions. It's a bit of a more general term. I'd probably use the term rational more than reciprocal. We have trigonometric functions, logarithmic functions, and exponential functions. These are our 7 prime functions of this module, and they'll take up at least 2/3 of our teaching time. But at the moment we're just looking at functions in general. So how do we imagine a function? So try and see a function as like a very simple calculator. It's got your input buttons 1 to 9. It's got your output, which is the screen, but it can only do one thing. Maybe multiply the input by 3 and add 4. And that's how we'd write that function. Here's my output, that's what appears on the screen. this is whatever value I feed in, and this is the kind of microprocessor. We could say add 6 to the input and divide this new value by 2. So these are what functions are. They're simple mathematical operations. And then we feed in inputs, we feed them into the function, and we generate outputs. We write these as coordinates, and then we draw a graph. So there's just a little picture of what we have. There's our input, x. There's my output, y. And in this case, we could say, what's the nature of the function? Well, the nature of the function is add 6 to the input and divide this value by 2. That's the nature of my function. And this bit, guys, is like a little microprocessor. This is we have 3 parts to our little calculator. The keypad is your input. That's when you choose what number am I going to put in. The screen is the output. And then we have a little microprocessor that's doing our sum. Now remember, each function will only do one sum. So if you wanted to look at 6 functions, you would need 6 of these little calculators. But that's kind of veering off the point a little bit. The little microprocessor determines what's done to the input. And often we want to just examine this bit. It's like we want to pull apart the calculator and see, well, what's going on in amongst in the chip, the electronic chip. So when we want to look at that microprocessor bit, the real nuts and bolts of the function, we use different notation and we call it fx. So now we're kind of behind the screen, behind the buttons, we're fiddling around with the electronics, and we're saying, well, what actually happens to our input? Well, it's multiplied by 3 and 4 is added. Or 6 is added to my input and then the new value is divided by 2. So this language here, guys, is really just talking about the engine of the function. What's happening to the input? So when you see that, don't be put off. It's really just pulling the calculator apart a little bit. Whenever we want to use the calculator, we snap it back together and we write them as a function like this. So usually functions, when we're examining the nuts and bolts bit, very often given f for function. But if you're looking at several functions, like I suggested, we need different functions, different calculators will need different labels on them. So G, K are often used, but any letter is used. Really it depends on the system we're examining. So we could have fx is equal to 2. Sorry, fx is equal to 2x. Our input is multiplied by 2. That's the that's the microprocessor bit. Now fx is just the name of it. There's our input, and then this is what's been done to the input. So now we're looking at the microprocessor. And if we feed in 0 as our input, our output will be 2. So this is just showing the function working. We're kind of testing it. And don't get too concerned about x. X again can change its letter depending on the system, but it's really just showing you your input. This is where the input goes. If I choose 2 as my input, anywhere where I see x, I'm going to put in the value 2. The letters change all the time. So like I said, f of x is 1 minus 2x plus x squared, could be written as g of a. Now a is my input, but it's the same microprocessor at work as up here. Or we could write it like this. So the inputs are changing and the name of the function is changing, but the microprocessor is the same. So all of these, even though they look completely different, are actually the same microprocessors at work. So the letters usually relate to the system we're examining. Be it motion or velocity, anything like that, will all define these letters. We could be looking at coulombs in a capacitor, any system is going to have its own kind of unique set of letters, and that's why sometimes people find maths so difficult. Most people would regard these as four completely different things, whereas actually they're the exact same thing, just with different labels. So if we're interested in, well, when my input is 3, what happens to my output? We would put it in like this, replace all the x's with 3's. And when you work that out, guys, this is 1 minus 6 plus 9. So that's 10 minus 6. Our answer is 4. Now, by the exact same logic, g of 3 would be 4, s of 3 would be 4, omega of 3 would be 4, because it's the same input being fed into the same microprocessor. We're going to get the same output each time. So it's really important in science, guys, not to be put off by the letters of the system. So Y is often used now. This is us looking at the microprocessor. Now when we snap it all back together again, so now we have our input, we have our output, and the microprocessor, we've rebuilt a calculator. Then we write it like this. So now here's my output, here's my input, and this bit here, guys, is f of x, our function, the nuts and bolts. What's happening to the input? It's been multiplied by 2. So our function from the last slide would be written, this is us just looking at the nuts and bolts, but now if we want to use x and y as our output and input, that function would be written like this. And essentially, guys, you can treat the two of them as the same thing. They're kind of saying the same thing. On the right is just more of a complete version of that there, So that's the nuts and bolts of the calculator. And this is the calculator in total with the buttons and the screen. So this one is obviously more useful. So when you're graphing functions, now we won't be doing this, guys, in a huge amount. I used to cover it in a lot more detail, but because I don't have the face-to-face contact, it's the learning outputs are not as useful. So, but we still talk about the philosophy, and we'll walk through it a little bit. So when you're graphing a function, first of all, you need to define, well, what's my domain? What inputs am I interested in? Then we use the function to determine the outputs. We feed these inputs into our function, and we get our outputs. Write the input and output as an ordered pair or as a coordinate. That's another word for an ordered pair. And they're plotted as follows. The input values always go on the horizontal axis. The output values always go on the vertical axis. It's very important, guys, not to make that mistake. If you draw your graph like this with the inputs on the vertical and the outputs on the horizontal, well, first of all, your graph is completely wrong, but you're really telling the world that you don't know what you're doing. So it's kind of a huge mistake in the world of science to mix up your axes. Like it's a good way of getting any research you do rejected instantly. And then we plot the line or the curve appropriately. Curve is more of a line, suggests it's straight, whereas a curve can be straight or have a bend in it, or several bends, as we'll see. So now we're just taking a look. Graph this function. Here's my inputs. There's the domain, what inputs I'm putting in. There's my range. There's my coordinates, as I discussed. And we plot these on a graph. So here's my horizontal axis, my vertical axis, and there's the point 0, 0. There's the point 1, 2. because that's 1, that's 2. Here we then have the point, there's 7. So notice how it's always the x value is first. 7, 14, and 10, 20. Finally then, we draw a best fit line. Now, another thing in science, guys, to be very careful of is this bit here. Don't always force the line through 0, 0. In many scenarios, we don't have 0 as initial condition. It's very common for your line to cross anywhere on the y-axis. Sometimes students from the Leave Insert seem to feel that the line must pass through 0, 0. This is absolutely not the case. So now we're taking a look, we're just going to take a look, guys, at some of the graphs we'll encounter. Now, we won't be drawing these. I have graphing software up on Moodle, so if you want to check out any functions, you can do it very easily and instantaneously using the software. So normally I would have made you draw out a little table like this. Here's my inputs. There's my domain. These are the input values I'm choosing. And this, guys, is my function. Here's my input bin squared. Now I multiply it by -4. And then I add 5. When I add these, I get my output. I do the same then for -2, for 0. And these now, guys, are ordered pairs. Sorry, -5, 50. -2, 17. These are what form our coordinates. Then we plot these on the graph as before. Always use a smooth curve, never join the dots with a straight line. That's called a polygon, and it's a different kind of way of analyzing than what we're using. So if you do need to draw a graph, make sure you use smooth curves if you're drawing a sketch or anything of a curve. I would often ask you to draw a sketch of a curve. Here's another function we're going to encounter, a cubic function. Again, the input is cubed, and then we're subtracting -4 times the input squared. There's the input cubed, and there's -4 times the input squared. Again, we get our coordinates. And in this case, guys, the curve looks like this. This is a typical cubic curve. So you can see it's very much a long way from a straight line that we saw on one of the previous slides. That shape, guys, is defined by that 3 up there. In the exact same way, guys, x squared will always give me that smiley shape. And we'll be discussing this again in a lot more. So that is the typical curve of any x squared function. This graph here is the typical curve of any x cubed function. So it's important to start to recognize the shapes. So when you see this cubed in a function, then you'll know the curve is probably going to look something like this. It's very important. One of the learning outcomes is for you guys to be able to relate a written function to its typical graph. So now we're just going to define a function in kind of a more formal sense. It's what differentiates a function from an equation. An equation is a function if every input only has one output. What this means, guys, is if we drew a vertical line anywhere on my curve, the curve would only cut the vertical line once. This is what verifies whether an equation is a function. So a vertical line is only cut once by the curve anywhere within the domain. So here we can see no matter where the vertical line is, It's only been cut once by the curve. So this graph here would be a graph of a function. So first of all, we've only got one output, so this is not allowed. Here we have our input, but it's an input and it's relating to two different outputs. Now that's possible with an equation, but it's not possible with a function. So if you had this scenario, then this would not be a function. And that's what it looks like, guys. This scenario up above, one input having two outputs, would look like this. So if you can draw a vertical line and it cuts the curve in more than one place, you're not dealing with a function. Then there's such thing as a one-to-one function, and that's if every input just has one unique output. So inputs can't share the same output. And this is verified by the horizontal line test. So we drop a horizontal line through the curve, and again the curve only cuts this line once. So we can see no matter where the horizontal line is, the curve only cuts it in one place. So this straight line is both a function and it's a one-to-one function. So different inputs can produce the same output. This is in lots of functions, but not necessarily in a one-to-one function. So this is a many-to-one function. This here is a one-to-one function, and we'll see some many-to-one functions in the coming slides when it's easier to look at it using a graph. If you do have a one-to-one function, if it passes both the horizontal and the vertical test, then that function definitely has an inverse. And we'll be exploring inverses an awful lot during this module. So again, guys, I'm only just laying the ground out. I know that you're probably scratching your head going, what's he on about? Like, it'll all kind of play out as we move along. So we'll just take a look at some typical curves you'd come across. Here's a circle. Is it a function? Well, when we do the vertical line test, you can see there's several places. A vertical line, anywhere on that circle, a vertical line is cut in twice. So a circle, guys, is not a function. So it can't be a one-to-one function, and it doesn't have an inverse. This is our quadratic curve. Is it a function? Well, we can see the vertical line is only cut once, no matter where it goes. But the horizontal line, when we drop down a horizontal line, there's loads of places again where different inputs can produce the same output. So we could say, we just say 2 and here. Both of these values are producing the same output. So this is not a one-to-one function, it's a many-to-one function. So that means it probably doesn't have an inverse. Some of them do. Here's our cubic function. Is it a function? It is, because everywhere the vertical line is only cut once. Is it a one-to-one function? No, it's a one-to-many. Again, one input. Sorry, no, it's a many-to-one. One input could have several inputs. All these inputs have the same output. So this is not a one-to-one function. Does it have an inverse? No, because it's not a one-to-one function. These are more the functions we'll be kind of examining in a lot more detail. This is a log curve. Now the only inputs are from any value greater than 0. So they're the only viable inputs. We check, is it a function? Oh, that doesn't, yeah, it's still, the vertical line should run. Is it a one-to-one? So it is a function. That vertical line, the curve only cuts it once. Is it a one-to-one function? It is. Does this curve have an inverse? Yes, it does. And that's a log curve, guys. Its inverse is 10 to the power of x, which will look like that. Here's a trigonometric curve. Is it a function? It is. Vertical line is only cut once. Is it a one-to-one function? You can see it's not. Several inputs share the same output. Does it have an inverse? This function actually does. Yeah, sine curve does have an inverse function. This, guys, is our last one. This is the exponential function. This is where we finished up kind of with no, sorry, we haven't got that far yet. I'm making a mistake. This is, yeah. So is this a function? Vertical line test. Curve only cuts once. It is a function. Is it a one-to-one function? Again, the horizontal line is only cut once everywhere on that curve. So that is a one-to-one function. So it does have an inverse. And its inverse, guys, is the ln curve. But we'll come to all of that again. So nearly every experiment, anytime you step into a lab and you're carrying out an experiment or a study, you're nearly always examining some type of a function. What you control in the experiment, be it time, I'm going to check my agar plate every 6 hours. You choose that time interval. So that's what you control. You could check it every 6 seconds. So whatever you control or choose, that's your input in the function. That's the x value, whatever you're changing. If you're changing the temperature and measuring how the length of a metal rod changes with various temperatures, you're controlling the temperature and you're measuring the extension in the metal rod. So what you change, control, is the input. What you measure is your output. And as I said, it's essential, guys, to not make a mistake between the input and the output. That's just what I'm saying there. It determines how we graph and interpret our results. So we just take a look at some data rather than kind of talking about things in a rough sense. We're looking at a scientist who's measuring the growth of a silkworm larvae and records the following data. So every 12 hours, the larvae has been measured. So time, guys, is our input. We are choosing the interval of measurement. How often are we going to measure this guy? Then the output, what we measure, is our output. And again, guys, these perform input, output. They produce coordinate pairs. So the input, guys, goes on the horizontal axis. The output goes on the vertical axis. Time is our input. Length is the output. So this is how you would set up your graph. These are our coordinates. So we would mark these then. Sorry. I don't know. Oh, I'm pressing the wrong button there. Okay. So if we plot this properly, this is what we would get. Notice again, time is on the x-axis, length is on the y-axis. And now we plot our coordinates. And we draw our line. And note here, guys, the line does not travel through 0, 0. So the larvae was, this is our initial, at t is equal to 0. The larvae was about 0.2 millimeters in length when we started the experiment. So that's what that value there, wherever your graph cuts the y-axis, the vertical axis, that's your initial conditions. And as scientists, we're always very interested in this. What's going on when t is equal to 0? Now, in the next lecture, guys, we're going to apply analysis to this. At the moment, we're just taking a look at how we graph our function. What we'd like to be able to do is develop a function for it. How do we graph it? At the moment, we only have data, but we'd like to be able to predict, well, what's going to happen in 2 weeks' time? You know, where's the graph going? How big will the larvae be in 2 weeks? How big would it be in 6 days, in 7 days? So that's what a function, once we get our equation written out, once we write out our function, that L is equal to something, 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 T plus something, something. Once we get that function written out, now we can start to use it to predict how the larvae will behave. But like I said, we'll come back to that in the next lecture. So a function can have one input. Here, Celsius is the input and Fahrenheit is the output. We'll be examining this particular function in a lot more detail over the coming weeks in lots of different scenarios. So this function, guys, changes. The input is Celsius. It changes Celsius into Fahrenheit. So what we can say is the microprocessor depends on whatever C value we put in. So F depends on C. We only need one input in this function. Similarly here. Here is a function. This is actually the function for the larvae on the previous slide. We'll talk about how this function came about in the next lecture. But here, guys, the length of the larvae only depends on time. The longer we leave it grow, the bigger it's going to be. Here we have a mathematical function. It's quadratic. There's only one input, x. I know x is appearing in a couple of different places, but there's still only one x to be put in. So we would now say y is a function of x, or y depends on x. So x, guys, these are the independent variables. We choose them. When we feed them into the function, we then get an output. So the output is called the dependent variable because it depends on the value of x or whatever. And then the input is called the independent variable because it doesn't depend on anything. It's simply the experimenter's choice. Now, lots of functions in science actually need several inputs. This is the function for kinetic energy. And here we need to key two inputs into our little microprocessor. We need to key in a value for mass, m, and a value for velocity in order to achieve an output. So E depends on m and v. Both of these are independent variables, but we need two inputs. Here we have a function. This is to do with the power from the wind, and it's got three inputs. The air density, the swept area of the rotor, and the wind speed. So here we have a function that needs three inputs to work. And again, we need three inputs just to produce one output. This output in this case is the power from the wind. So our input, independent variable, output is the dependent variable. Finally then, guys, we're nearly there now. Many simple functions are directly proportional. These have only one input term, and the symbol for proportional is this. It's like an infinity symbol with the end chopped off it. You can use this symbol the exact same as an equal sign. So when I say a simple function, guys, here we have the circumference of a circle. A simple function, guys, only has one term on the right hand side. So our input, there's only one term. We have one input, but there's only one bit to feed into. So we could say now C is directly proportional to R. The area of a circle, A is pi r squared. Again, there's only one term on this side. It's not pi r squared plus 2 pi r h or anything like that. That's the area of a cylinder. This is just the area of a disk. So now we would say the area of a disk depends on r squared. A is proportional to r squared. We have the volume of a sphere. And here these are a constant value. That's a constant. These are constants. So V depends on r cubed. V is proportional to r cubed. Now, when we only have a single term on the right like this, these are the only scenarios where your graph will pass directly through 0, 0. We'll just say we make that R. And say this is obviously BC because it's a straight line. So all the graph is saying is when the radius of a circle is 0, then the circumference is 0, which kind of makes sense. You know, same as if the area of a circle is 0 if the radius is 0. So essentially, guys, when you have a single term on your input side, you are going to get one of these proportional graphs. And these, in a way, are our favorites because they're the easiest to analyze, which we'll be looking at in a couple of months' time. Definitely after Easter, anyway. So like I say there, we'll explore this more as the module progresses. So that finishes us, guys, for the first lecture. So thanks for listening, and we'll finish it up there.